So,
Ah,
so good evening, guys. As I was saying, we'll cover alkaloids, and we'll be using Dr. Nelly Mungai's slides. So we've covered other series of secondary plant metabolites, the likes of glycosides, and we saw that we had different classes of glycosides. Now we'll have another class of secondary plant metabolites, that is alkaloids, and it's a bit bulky. So yeah, so when you have alkaloids, you have these chemicals or compounds that you should have them in mind, like morphine, codeine. So these are narcotic analgesics that are derived from plants which have alkaloids. So alkaloids connect the dots, narcotic analgesics such as morphine and codeine. Haya. So those are the various learning outcomes of alkaloids. So we'll start from this first slide. That I'm saying that plants that usually have alkaloids, they vary in both the taxonomy and chemical nature. But we have nitrogen as the unifying factor that cut across all the different classes of alkaloids. So we have different classes of alkaloids. We'll see later on in the discussion. We'll say that all the classes of alkaloids will have nitrogen group on them. So yeah, so that's basically what's on the first slide. So we should note that most alkaloids are very toxic, and that's why they do not feature prominently in herbal medicine, but they're very important in allopathic system, where you usually minimize the dose. So since these plants are very toxic, and they have very low therapeutic window, so you'll have to be very careful with the dose that you administer as in the allopathic system. So also in homeopathy, dose rated is extremely low, as I've said, it is very toxic. So point to note, alkaloids are very toxic. That's why their dose are usually strictly controlled. Yeah. So what is an alkaloid? So the word alkaloid means alkali-like, and this is a bit of history that was discovered by a pharmacist. This is the guy. So these are the different chemicals or compounds that are derived from alkaloids. So we have nicotine that was discovered in 1803, morphine in 1816, strychnine and emmetine. So this emmetine, it's very common in the body exam questions. Emmetine, we'll say that it's one of the most common alkaloids derived from a plant that usually has a problem, most of us, in the pronunciation. So these are the most, let's say, most common chemical compounds of derived from alkaloids. So you can just take a few seconds to get them. So I've said nicotine, morphine, strychnine, and emmetine. So the word alkaloid is applied to a basic nitrogen. So containing compounds of plant origin. So they may contain one or more nitrogen atoms, that is in heterocyclic ring. Yeah, that is what we've said above here. Alkaloids, usually they have They are different both in taxonomy and chemically, but the unifying factor is a basic nitrogen group, which is usually cut across all the different classes of alkaloids. So maybe that's one of the unique things that you should know. That alkaloids, they have a nitrogen atom. So I've seen that most of them are found in plants, but we have others that they are in animals. So alkaloids usually are very complex in their molecular structure, and they manifest significant pharmacological activity both on man or on other animals. So the term protoalkaloids or aminoalkaloid to compounds like codeine, ephedrine, colchicine, which lack one or more of the properties of typical alkaloids. So you're seeing these compounds here, the three of them. Let me try to highlight so that at least the slides can be a bit beautiful. So in this statement says that codeine, ephedrine, and colchicine, they lack one or more of the properties of the typical alkaloids. We'll see the properties of typical alkaloids in the next slides. So the three properties may lack one or more of the properties of typical alkaloids. So, yeah. So we have synthetic compounds such as minutes. Yeah, these three compounds usually are unique because they do not have either of the typical properties of alkaloids. So we have synthetic compounds such as homoatropine, which are not found in plants but closely related to natural alkaloids. So homoatropine is not found in plants. So we are going to see the distribution of alkaloids in the plant kingdom. So alkaloids have the distribution in the plant kingdom, and the distribution in the angiosperm is uneven. So these are some of the families that have an outstanding in the production of alkaloids. So we have these 1, 2, 3, 4, 5 families that that have outstanding in the production of alkaloids. Yeah. So unique features about these families, Labiatae and Rosaceae families are almost free of alkaloids, so they do not have alkaloids. These families, the two families here. So let's say they're not important in alkaloids. So most occur in the cotyledonous family, but some in monocotyledons. Sawa. Haya. So the next thing we are seeing that alkaloids are nearly absent in the algae or in the lower groups of plant kingdoms, with the exception of agate, alkaloids, and the various mushrooms. So let me highlight this. So agate alkaloids and various mushrooms, they're usually found in the lower groups. So these are the only exceptions that where you find alkaloids in the lower groups of the plant kingdoms. So, so we also seeing another thing here where some of these alkaloids also occur in skins of amphibians together with other toxins. So we have the philobates, which is a very neurotoxic alkaloid that are found in frogs. So maybe it's unique. It's a unique thing that you need to know that phyllobates is one of the potent neurotoxic alkaloids that usually found in frogs. Mm. Mm. So here you'll have to to know these the sources of these alkaloids. So usually saying that the currents of alkaloids in a plant does not appear to be confined to certain specific organs of the plant. So you'll find some of the alkaloids they occur in a bark, some in the root, some in fruits, and some in seeds. So you'll have to at least know this one. This one you'll have to know that chinchona is found in the bark. Aconite is in the roots. Conium and black pepper is in the fruits. And then areca nut is in the seeds. So I'll give you maybe half a minute so that at least you can appreciate that. Then we continue. So guys, that's it. So I other um yeah other alkaloids that we've seen that belladonna occurs in the leaves, and then this the one that I was telling about that produces the emitin, and then we have hydrastis that occurs in roots and rhizomes. You think that also tobacco produces alkaloids in the roots and usually translocates them to the leaves where they accumulate. So alkaloids in tobacco, they're usually in the roots, but they are, let's say, transported to the leaves where they usually accumulate. Then we have this Papaver somniferum. So this family where they occur in the latex of the fruit. Yeah. So set of the alkaloids in the plant, so they may exist in the plant in the free state as salt or as amines or as alkaloids in the end oxides. So these are the various states where alkaloids usually exist. So we have the free state, we have the salt state, or as amines, or as N oxides. So these are the different states where alkaloids exist in plants. So you'd say that is free state, salt, amines, or N oxide. So the degree of basicity of alkaloids, usually the degree of basicity they vary based on the structure of the molecule and the presence of and the location of the various functional groups. So this is just basic knowledge. So alkaloids usually the primary nitrogen. This is the primary nitrogen. They are usually very basic. So an example is mescaline. So primary nitrogen atom, it's very basic. And then mm, as you go down, like from primary, secondary, tertiary, quaternary, the basicity usually I think should reduce. Yeah, I think should reduce the basicity of that alkaloids. So primary alkaloids, very basic. Then we go to secondary nitrogen atom. Sorry. Yeah. So the main point is, as you go down, like from primary, secondary, tertiary, quaternary, the necessity of the alkaloids usually reduce. So we've been given an example. The primary nitrogen, that is mescaline. For the secondary nitrogen atom, we have ephedrine. Tertiary nitrogen atom, we have atropine. Quaternary, we have toluene. So um, alkaloids. Alkaloids, we said that they occur in different forms. One of the forms is salts of acetic acid. We have malic, oxalic, tartaric, acidic. Yeah, sorry about that. So it said that alkaloids, they occur in different forms. As we said, it occurs in free states, so as salt, as amines, or as alkaloids of N oxide. So I've seen that from that statement. So these are the different forms of salts of alkaloids. So we have, for example, we have the acetic acid, we have the malic acid, oxalic, tartaric, succinic, tannic, and any other plant acid. So in some cases, these alkaloids usually they are combined with special acids such as this compound aconitin, which they form aconitic acid. So it's a combination of aconitin and aconitinic acid. That's why this statement is saying that usually they occur in combination with acids. So opium alkaloids, we have meconic acid, the chincona alkaloids, we have the quinic acid, and then also we have other alkaloids that are usually in combination with glycosides, which forms compounds that are called glycoalkaloids. So example, so is a combination of glycosides with alkaloids. So hence this name glycoalkaloids. So an example, we have solanine, which is found in root tubers. So kindly remember this solanine that is found in root tubers, in the potato tubers, sorry. So these are example of glycoalkaloid. So kindly just remember this important alkaloid. So as we talked about in glycosides is a combination of glycol, which is the sugar moiety, and a glycol, which is the non-sugar moiety. So it's seen that solanidine is a glycol, which is a non-sugar moiety. Can have a mixture of sugars forming with glycosidic leakage. Let me see what's saying here next. Yeah. Mm. So, so we have function of alkaloids in the plants. These are the four main functions. So against protection, so they protect themselves because they're very poisonous agents. As I introduced earlier, we said that these alkaloids are very toxic and harmful. Hence, their dose is usually very regulated because they are harmful and toxic, and they are very limited in terms of their use in the herbal medicine. So the end products are usually of detoxification due to reactions in the plant. I'm not getting this. End products of detoxification due to the reactions. I'm not getting this function as a function. Number two, so and the other function is regulatory of growth factors, and also they could serve as substance capable of supplying nitrogen and other necessary elements. So you've seen that alkaloids, one of the unifying factor of alkaloids that cuts across all the classes of alkaloids is saying that it's nitrogen. Kindly remember that That's why this is one of the function of alkaloids, supply of nitrogen and other necessary elements. So the nomenclature, this is how basically you name the alkaloids. So alkaloids, all alkaloids have these I in their name. So an example, we have a generic name of the plant atropine, which you get from atropine belladonna. So, and then hydrastine. So this is the alkaloid then you find from this species, hydratis species. And then another way we have the specific name of the drug. So example, we have cocaine, which is from coca leaf. So, and then we have physiological activities which this emitting. We'll see it later in the classes of in one of the classes of alkaloids. So emitting from this plant, ipecacuana. So as I've said, this one you can't miss it in any of the revision papers. And then also have nicotine. So summary in this slide, you're saying that alkaloids, all of them, they have this suffix "ine" in their name. So the example that we've stated, they have atropine from atropine belladonna, hydrastine. As you've seen, we have this "ine" from this species, hydratis species. And then we have seen cocaine, we see also INE from coca leaf. And then you also have emetine from, now this is because it's an antiemetic, because that's why we have the physical activity here. So yeah, and then the other way of nomenclature, maybe from the physical property, we have hygrine from the word hygro, which is basically means moist. But you're also seeing the suffix "in" here. So we also have another way of naming these alkaloids apart from these other. So we said that the generic name of the plant, that's one of the way of naming the alkaloids, but it ends with "in." So atropine from the plant atropine belladonna. So that's where we get these alkaloids. Then we have hydrastine from this plant, hydratis species, and then have the specific name of the drug. So we have cocaine. We know cocaine is a drug. So from this plant coca leaf, and then the physical activity. So you're seeing that emitting, it is used mostly in to stop nausea. So this is the physical activity from this plant. And then we have now at physical property of the nani of that alkaloid, which is hygrine, and it says that it comes from hygro, which is moist. And then the discoverer, no, this is the person who discovered these alkaloids. So we have pelletrain, which is after pelletire. So any one of you, if this even of you gets a chance to discover an alkaloid, they'll have the name "in" at the end. So yeah, and then common name of the drug healing the alkaloid. So we have agotamine. So agotamine is one of the agate alkaloids, and we've seen that one of the unique features also of these alkaloids, as I stated above, that they do not occur in low family species apart from these agate alkaloids. So remember that. So we have the physical properties of alkaloids. So as I introduced earlier on, we have a class of alkaloids that they do not have either one or more properties of the typical alkaloid. So we come back here again. So we have these compounds which lack one or more of the properties that I'm going to discuss next. So let's revise this. So we said we have adenine, ephedrine, and colchicine. So these compounds, they do not have all the properties of typical alkaloids. So can you remember that? At least maybe if it's this other name is a bit difficult, we have at least ephedrine and colchicine, which are very common drugs. So remember that. So can you remember ephedrine and colchicine? They do not have any. They lack either one or more of the typical properties of the alkaloids, which I'm going to discuss now here. Yeah. Mm. So these are the general physical properties of alkaloids. So alkaloids are usually odorless, colorless, crystalline, and volatile bitter solids. So this also, you see, these properties usually cuts across also maybe a solution of glycosides, except some usually colored. You've seen that in glycosides, we saw anthocyanins, they're usually colorful, and then others, most of them in glycosides are bitter, but we also saw some that were they had like they were not bitter. So at least these property you'll find them also some in glycosides. So or also seeing that few here are colored. For example, you have berberine and colchicine, which is yellow, canadine, which is orange in color. So berberine and colchicine, they're yellow. This one you just have to cram. Berberine and colchicine is yellow, and then canadine is orange in color. So colorless alkaloids, however, may also have colored salts. Also, as a revision, it said that alkaloids, they usually occur in different forms. It said that some may be salts, some yes, amines, and the rest. So let me just take you back to that also slide that I was discussing as a revision. It's here. So yeah, so it's saying some of the alkaloids may exist as free state salt, as amines, or as an oxide. So these are the different states which alkaloids occur in plants. Again, I repeat: free state salt, amines, or an oxide. So yeah. Then we saw different repeat, sorry. Yeah. So saying the occur as colored salts such as hydrastin, which the source is this hydratis caridensis. Yeah. And the salts are yellow. It's also saying another salts here. So this word here, which is copper red. Yeah. Some alkaloids are usually liquid, such as nicotine, conine, or pilocarpine. Others are amorphous, such as emitin, and most alkaloids have at least one oxygen atom in the molecule. So this is an example of a structure of hydrastin. So we've seen that the unifying factor, we have a nitrogen. We said nitrogen cuts across all the classes of alkaloids. We have a nitrogen, and then you've seen here, oh my God. Yeah, so we have seen also the last statement that most alcohols at least they have one oxygen atom in the molecule, but this one has two. Yeah, it's not true. They are six. Higher. Continuation of the properties. Nicotine and conine are example of alcohols that lack oxygen atoms. So hii lazima ukram sasa. Maybe inaweza kuwa MCQ. So nicotine and conine are alcohols that do not have oxygen. We've seen that most of them, they have oxygen, but these two, nicotine, at least nicotine is common. It forms in most of these lift ama velo. It's found there in that drug. So at least mkumbuke na hiyo nicotine. Ukiona mtu anatumia velo lift, kikujia kwa pharmacy, ukumbuke haina oxygen na wana inhale. Maybe hiyo itakumbuka, it will help you remember that property that nicotine and conine did not have oxygen. So yeah. So they are in terms of solubility, that statement there, it's not that important. So they usually administer in form of solution. So the differences in solubility comes in, so between alkaloids and the salts. So these the solubility between alkaloids and the salts, they usually now provide a method of the solution from the plant and solution from the non-alkaloid substance present in the plant. So we'll have different, in the next slides, we'll see extraction of alkaloids. So this is one that we'll use these bases in order to isolate these alkaloids from plants, basically extract. Yeah, so the solubility of alkaloids and their salts usually show considerable variation because of the extremely varied structures. So free bases are usually fairly soluble in organic solvents such as chloroform and ether. And they are usually insoluble or sparingly soluble in water. So you can almost say that alkaloids, they're fairly soluble in organic solvents and insoluble or sparing soluble in water. So alkaloid salts, they are soluble in water and insoluble in alcohol. So alkaloids, when they occur in their own form, they are soluble in organic solvents and they are insoluble in water. But when they occur in salts, they are soluble in water and less soluble in alcohol. So it's the opposite of the other. But you know that a salt is it's an organic, so you know that yeah. Ukishika moja kama ita confuse zingine, just shika moja so that you know that alkaloid in their own nature ziko soluble in organic solvents and insoluble in water. But the opposite now in the salts, it's the opposite. So you think that an example, strychnine hydrochloride is much soluble in water than strychnine base. So hapa the light dissolves light is not, it's not nani, it's not happening. So exceptions, they have caffeine, the base, it's extracted from tea with water. So colchicine is soluble in either acidic, neutral, or alkaline water. So alkaloid salts, quinine sulfate, sparing soluble. So 1 part is in 1,000 parts of water. Quinine hydrochloride, very soluble in. So there's an example. But the baseline, we said there hapo juu that alkaloids are soluble in organic solvents, but not soluble in water. But the salts is the opposite now. So we go to isomerism. So many of these usually they show optical activity because they contain one or more asymmetric carbon. So in most cases, we have the level usually exhibit. It has the pharmacology activity compared to the dextro isomer in the same alkaloid. So if you have an alkaloid, let's say atropine, but this is just an example. So if you have an atropine which is in the level isomer, and it also has the dextro isomer. So the one that has the level isomer usually is the one that has a greater pharmacological activity compared to the dextro. So also have an example here. So an example, we have ephedrine L, which is the level L level isomer, is has an activity of 3.4 more, has 3.5 more activity compared to the D ephedrine. And compared also to L agotamine, which is 4 more times active compared to the D agotamine. So that's another point to note. So L usually exhibits a greater pharmacological activity compared to the D, LD. But there are few exceptions. Again, as I said, alcohol is a bit complex. So we have tibocurarine, which is is medicinally. So these are things that compare. So you're saying that the D is more active compared to the L in this compound. Sawa. And then also we have quinine. Quinine are both useful alkaloids. So quinine, as we know, that is an antimalarial, and then quinidine is used in arrhythmias. So these are exceptions that where the D usually exhibits more, or you can say rather than it has a greater pharmacological activity compared to the L. But in real sense, L usually has a greater. Let me just go back to that slide so that when I'm talking, you have at least a pictorial image in your mind. So in this slide, you're saying that the L usually exhibits a greater pharmacological activity compared to the dextro. But now we're saying that there are few exceptions such as quinine, tibocuranin, and quinidine, which the D now is more active compared to the L. Yeah. So we have, I think, 3 methods of extraction of alkaloids. Yeah, so there are 3 I've seen here. So the general method used usually based on the alkaline nature of most alkaloids and the scientific ability to form salts with acid. Yeah, so when as we discussed above there, this is the one that usually give us the leeway to isolate these alkaloids because of the ability to form salts and the alkaline nature of these alkaloids. So, and also on the relative solubility of the alkaloids, bases, and the salts in water and in various organic salts. Haya, revision tena tumesema alkaloid in their own form, we say that they are soluble in organic solvents, but they're insoluble in water. But their salts, the salts are opposite of what I've just said. So say that upper alkaloids are soluble in organic solvent. Salt, it is not so. It's the salt is insoluble in organic solvents and soluble in water. But here is the opposite. So the first procedure, or you can call procedure A, as it's stated in the book. So just read. So in all the extraction procedure, it is important to powder the plant material to facilitate effective contact of the solvent to alkaloids containing the tissue itself. So in order to facilitate smooth extraction of these alkaloids, you need to powder first. So you convert the raw, the raw nani into powder. So you powder it so in order to have enough contact with the solvent. So then the powdered plant material is defatted usually with petroleum spirit or pet ether. And then because alkaloids usually occur in the plants mostly as salts, so bases are liberated from the salts by addition of ammonium hydroxide solution. And then the ammonium hydroxide solution is sufficient basic to liberate most common alkaloids with minimum difficulty. So the first process is that you powder that plant in order to have effective, in order to have an effective contact with the in order to have effective contact with the solvent, so that these tissue cells ziweze kupata hiyo contact. So that's the first plant, powder, and then use petroleum spirits or ether to defat the plant material. And then after that, you add ammonium hydroxide. So this ammonium hydroxide solution usually is able to liberate the alkaloids. So once the alkaloids are liberated, they're extracted using an organic solvent such as chloroform. Haya. So hapa tumesema powder, plant material. So then that's the first step. Powder, why do you need to powder? So that that plant, the powder, should have enough contact with the solvent. Sawa. And then after that, you defat with either pet ether, sawa. And then you add this ammonium hydroxide so that you may liberate the alkaloid. So after you liberate the alkaloid, you add what? Chloroform in order to extract it. So then so when this, so why Alkaloid mixes combined salts separate. So yeah. So now you also after that you dilute it in sulfuric acid in order to convert the bases to salts. So you separate the organic layer from the aqueous layer containing the alkaloid. So you discard this. So yeah. So after this step, you dilute it with sulfuric acid. So once you do that, you usually convert it to salts. And then if you have salt, you'll have two layers. So you separate the organic layer from the aqueous layer containing the alkaloids layer, the alkaloid salt. So that's able to to get your salt. Mhm. So these are nice. So you continue with the step actually. So after you get the alkaloid salt, you add again ammonium hydroxide in order to convert to base. And then you add chloroform, then the alkaloid bases in chloroform separate with two layers and then discard. Hey, this one is too long, man. You'll have to read on your own in order to understand. I'm sorry. Yeah. So you get there, you add chloroform, then after adding chloroform, you have two layers again. So you discard the aqueous layer, you have the organic layer. With the organic layer, you add again dilute sulfuric acid. So after you've done that, you get another two layers. You get the alkaloids that are going to be in the aqueous layer, and you have an organic layer. So you discard the organic layer, you remain with the alkaloid layer. So so that was method one. This is method two. Method two, basically you extract with water, that is miscible solvents. So most of the alkaloids and their salts are soluble in alcohols such as methanol, ethanol, or isopropanol. So we can use these solvents to extract alkaloids from the plant. So you have to extract 4 times in order to exhaust all the alkaloids in the plant material. Sawa. So other non-alkaloid materials are extracted along with the alkaloid cells. The extract requires purification to separate the alkaloids from non-alkaloid material. So you need purification in order to separate those other compounds that are not alkaloids. So we have the non-alkaloids that we're talking about. We have an example of tannins, which are precipitated with lead acetate. Yeah. So the precipitate of tannins is washed with the extracting solvents to recover any alkaloids. Yeah. So basically, that's what you're saying. Once you have done the 4 consecutive extractions, you make sure that you purify that substance that you have gotten in order to make sure that you've gotten only alkaloids. So the last method, we have extraction of alkaloids with acidified water. So as a recap, we said there are three. There are three methods. We started with the one that it was a bit long. Yeah. And then we went to the second one that we used water. And then now we are using acidified water. So acidified water can be used to extract the drug. And then the next thing said that acidified water takes an alkali salts in the drug or converts the bases into salts, which then go into the solution. The extract is then made alkaline, and then the alkaloids are removed with the immiscible solvent. The alkaloidal extract in the immiscible solvent is then shaken with an acidic solution. Then you add the dilute sulfuric acid over, dilute sulfuric acid is the one that is preferred compared to hydrochloric acid. because certain alkaloidal chlorides are soluble in chloroform. Hey, this one, well, you have to read on your own because that time I'm not getting it. Yeah. So then we have subsequent conversion to bases and extraction with organic solvent that will help in the purification of the extract. So the alkalis in the organic solvents and then dried over anhydrous sodium sulfate, and then the solvent is evaporated. So in order to avoid formation of trouble, some emulsion after addition of solution to is that it. So you add this ammonium hydroxide solution in order to avoid formation of emulsion. And then crystallization of the alkaloid salt can be done by addition of suitable acid. So these are just a diagram showing that. I don't think we'll cover that, but we can. We have to do identification. Yeah, how can we identify alkaloids? So you can identify alkaloids with their melting point, suitability, X-ray, crystallography characters, the color reaction, UV and I spectra, and optical rotation. So that's the different ways of identifying. So we have also other characteristics and properties of alkaloids. So alkaloids usually, we say that the unifying factor is nitrogen atom. So at least you have a nitrogen atom, but we have exceptions. Agotamine may have up to 5 nitrogen compounds. The other thing that we'd seen that most of these alkaloids, they have oxygen atoms. We said that nicotine is an exception. It does not have, it lacks oxygen. So the nitrogen atom usually exists in heterocyclic ring. So we have like these alkaloids such as ephedrine, mescaline, and colchicine. The nitrogen atom is not in the ring, but as a surgeon. So these exceptions are a bit many. These amines exhibit a aliphatic character. The nitrogen usually occurs in a tertiary amide form in which only 2 bonds are involved in a ring. That one is biochemistry, you need to know that. Maybe you need to know this. Or as I mentioned just a few minutes, some alkaloids like oxygen in the atom. In the structure, we said that we have nicotine and quinine, and we have that the other one that we said that you need to cram. So we have quinine and nicotine. Usually volatile liquids, and also remember that they also lack oxygen atom. So pilocarpine and arecolin are oxygenated but exist as non-volatile liquids. Sawa? It said that alcohols are basic because of nitrogen, but the basicity usually vary depending on where the N attaches itself. So it said that primary are usually very basic. As you go down this, the basicity decreases. So alkaloids, since they are basic, they can be neutralized with acids. That one is straightforward. Some are amphoteric due to differences of acidic groups like OH. So morphine has an OH group and a carboxylic group. Morphine has an OH group, and then we have a carboxylic group in this narcissine that usually make them to be amphoteric. So few alkaloids usually possess weak basic properties, and their salts are not usually stable. So we have this piperine, papaverine, and caffeine. They are they are very weak. So these are a structure of quaternary alkaloids. These are just continuation of properties of alkaloids. So you go to test for alkaloids. There are four, I think, but you just go on. So we have this test. We have Mayer's test, where the combination of mercuric iodide and potassium iodide in water, it gives white to creamish precipitate with alkaloids. So I'm in the presence of alkaloids, we'll have white to cream precipitate, the Mayer's reagents. And then the Wagner's reagent, it's a solution of iodine in potassium iodide, which gives a white precipitate. So we have another one here. And then for the Hager's reagent, so we have a saturated solution of picric acid that gives a yellow precipitate with alkaloids, and then tannic acid gives a white precipitate with alkaloids. So you've seen that only the Hager's reagent that gives a different color. So Mayer's reagent, Wagner's, Hager's, and tannic acid. So I'll give you like 1 minute, you look at it. Sir, so as I think you have seen that. So let me just repeat. So we have the Mayer's reagent, Wagner's reagent, Hager's reagent, and tannic acid. So with these four, the Hager's reagent one that is unique because it forms a yellow precipitate, but the rest they form a white precipitate. So we have the Mayer's, Wagner's, Hager's, and tannic acid. So usually alkalis, they have different color reactions, but they're not specific, because it's seen that as such only minute quantities of alkaloids are required to give the expected color responses. So these color reactions depend on the hydration or oxidation of alkaloids to give the characteristic response. So yeah, so alkaloids, because alkaloids undergo various color reactions, it may not be very specific or sensitive. That's what you're talking about. So these are the most specific ones. So the one that you have stated, they just give color reactions. So these are the ones that they are a bit more specific. So we have the Marquis reagent, that usually you add 2 to 3 drops of 40% of formaldehyde with 3 ml concentrated sulfuric acid. Sorry. And then we have the Mandeline's reagent, which you get about 1 gram of finely powdered ammonium vanadate, which is dissolved in 200 ml of pure concentrated sulfuric acid. And then you have the mix reagent, where you take about 1 gram of selenic acid that you dissolve it in 200 ml of pure sulfuric acid. So as you've seen here, sulfuric acid is commonly used here, you see. And then we have this, which is so hard to pronounce for me. So this reagent is only used as a spraying reagent in paper chromatography to detect the presence of alkaloids in chromatograph. So the unique feature about this, it's a spraying reagent. So these are the four that they do not use color. Remember the first four, usually we're using color to determine the presence of alkaloids, but you've seen in the next slide, they're saying that they are not quite specific. So the one for colors, we say that you have the Meyers, Wagner's, Tannic, and Hager's. But the one that uses at least specificity, we have these four: the Marquis, Madeleine, Mex, and the last one. So yeah, maybe I'll give you 1 minute to look at it. Aya, sawa. So we go to the next thing because of time. This is just a continuation of the previous slides. So we have the Drangendorf's reagent. It's saying that this is the procedure to perform that test. So stability of alkaloids usually the generally decompose upon heating. It's a few sublime without decomposition, for example. So we have some that they sublimate and others they just decompose upon heating. So we have caffeine when subjected to that heat 70 degrees Celsius for a long period of time, usually which forms the basis for testing for caffeine, which does not precipitate like most of the alkaloids. So it is detected by mixing with a small amount of potassium chlorate and a few drops of HCl, and then it is evaporated to dryness, and then you expose it to residue of ammonia vapor. So after that, it will form a purple color. So we have, so we'll repeat that. So this Murexide test, it's a test for caffeine. It's in that most of these alkaloids usually decompose upon heating, and some they sublimate. So they sublime without decomposition. So we have this test, Murexide test for caffeine is subject to 70 degrees heat for a long time of period, and then after this it does not precipitate. Hata kama ukihit, it does not precipitate. So you mix it with a small amount of potassium chlorate and a few drops of HCl. And then after evaporating, you expose the mixture to ammonia vapor. So it will form a purple mixture. No, a purple color. So this purple color will confirm the presence of caffeine. So caffeine, usually you confirm the presence of caffeine with Brexit test. So another alkaloid. So strychnine is one of the alkaloids that can stand heat treatment. Glutamine becomes easily destroyed when exposed to heat. I say that many alkaloids are usually strongly basic. Most of them will form. So this is just repetition of what you've just been saying above here. So there's a question in preparation of salts of alkaloids called solutions of the minerals acids are used. And then when you heating or using acetic acid may bring about other profound changes. So these are just so these are just the other important notes that are repeated mostly above there, what we've just covered. So we have structures of alkaloids and the classifications. So alkaloids have diversity in their nature, in terms of botanical origin, the chemical structure, and pharmacological actions. So in terms of pharmacological actions, we have the non-heterocyclic alkaloids. Usually, they're called atypical alkaloids or protoalkaloids. So non-heterocyclic alkaloids. So I also saw this mescaline somewhere that they don't have one or more of the general properties of alkaloids. So I think we take a break and then we continue with the part 2 of alkaloids, which is now what is the most important part because now covers the classification of alkaloids. We'll take a 5-minute break. So we'll be back at 2040. Sam, Sam.
Hello.
Oh, nice, nice,
Hi.
nice. Niliambiwa Hai, pole sana. Nilimwambiwa unajisikia ku take from part 2. Uko na content unataka ku spew. So let me take over from. So let me continue. Once Sam gets back with his internet, we take over from where I have left. So we started the structures of alkalis and the classifications. We said that alkalis are very diverse in their nature because of their botanical origin, the chemical structure, and the pharmacological activity, the action I mean. So we said that one, we have the non-heterocyclic alkaloids, which are also known as atypical alkaloids. Sorry, atypical alkaloids or protoalkaloids or biological amines. So you have an example of mescaline. Mescaline is an example of an heterocyclic alkaloid, also known as a typical alkaloids or a protoalkaloid. So protoalkaloids are examples. We have ephedrine, caffeine yenye tunakunywa, conosine. These are example of protoalkaloid or non-heterocyclic alkaloids. So these are just examples of classifications. The other part we have now heterocyclic alkaloids. Just a minute. A minute. Let me just. Sam umerudi?
Yeah, niko poa.
Sawa. So you'll share. Nilikuwa nimeweza tu part 2.
Thank you. Uh, yes. So my screen is visible to you guys.
Yeah, iko sawa.
Nice. So yeah. I'm really sorry I came in late today. Uh,
Yeah, we can hear you.
uh, Alkaloids 2, botanical origin, chemical structure, and family. Alkaloids 1. So, for example, plant families from which we have the Solanaceae family. We have yeah. So in terms of chemical structure, we have the indole alkaloids, the indolizidine, yeah, and etc. So there are so many different chemical structures from which alkaloids are derived from. And in terms of pharmacological so we have different, for example, in the quinine alkaloids, we have the quinine itself, which is used for malaria. We have quinidine, which you saw has been we have this special type of the ring structure. So if they lack the ring structure already, but they have the other properties, say they're alkaline and they have the basic nitrogen somewhere in their structure, then we refer to this type of alkaloids as protoalkaloids or atypical alkaloids. And an example is mescaline. Yeah. From this diagram, you can see mescaline actually has the aromatic structure, but the amino group or the amine group is not actually in the ring itself. It's actually found on the side chain. Same thing with ephedrine. So caffeine is a special example because in as much as they have a nitrogen ring on the yeah, they have a nitrogen group on the aromatic ring. They are considered neutral alkaloids, and the reason for that is they're not really derived from any amino acid. So usually, I think it was discussed in alkaloids 1. Alkaloids usually have very specific definitions. So they have to at least be derived from a certain amino acid, and mostly it's usually the L-type forms of the amino acid. And also there should be the nitrogen in the heterocyclic thing. But for caffeine, we actually don't derive it from any amino acid. And that's why it falls under this category. Steroidal amino acid and as well as steroidal alkaloid. So actually, ephedrine has various clinical uses. I think hope you guys are with me. Sorry, I don't know why it keeps on logging me off. Am I audible?
Yes.
I'm really sorry. I think it's my network. I'm not really sure what's happening. Okay. So over here, they're telling us heterocyclic alkaloids, or the typical alkaloids, usually contain nitrogen in the ring. And many alkaloids in this group are divided according to the ring structure. So we look at the type of ring. If it is an indole, if it is an indolizidine, then we'll basically name them according to the chemical ring structure. So they're classified according to the basic nucleus, that is the ring, from which they're derived. So we have a couple of classifications over here. And the first class that we look at is the pyridine, or the piperidine examples. So the examples over here are choline, lobeline, quinine, and nicotine. Just briefly to mention the chemical uses. Okay, quinine is usually a poison, and I think you've come across it as, yeah, it was actually drunk, the one from Conium maculatum. It was drunk by, was it Socrates? Yeah. Nicotine, as you know, is found in tea and cigarettes, basically CNS stimulant, and same thing with lobeline. So the structure is usually either derived, especially for nicotine, you'll find it has pyrrolidine core or nucleus. So it was actually derived from it. Lobeline is actually from the same group. So we have other groups such as the tropane alkaloids. The nucleus will be the tropane itself. For the quinoline alkaloids, for example, quinine, quinidine, cinchonidine, they usually have the quinoline nucleus. And yeah, so basically that's, so for the purine, we have an example of caffeine, as we saw Aponyuma. So for piperidine and pyrrolidine. So piperidine is usually a 6-membered ring with a nitrogen group. So there are no double bonds anywhere in between. And for pyrrolidine, we have the structure having a 5-membered ring with only one nitrogen and basically no pi bonds in it. So maybe the only pi bonds can come from the lone pair of electrons. So for the tropane alkaloids, so an example of the piperidine and pyrrolidine, we have basically lobeline, nicotine, choline, the ones we mentioned up there. So tropane alkaloids, this I think are the most common and most diverse group over here. So basically, their central core is usually the tropane nucleus. And over here in hyoscyamine, you can actually see it on the left part, this rectangular shape with nitrogen and a methyl group, and also in cocaine. So we usually have a lot of them. Atropine itself, yeah, so they're usually the most diverse in terms of the family, but they're mostly derived from the Solanaceae family. So the atropa alkaloids usually fall under the tropane alkaloid group, basically. So, okay, I think you know cocaine is actually a CNS stimulant. Hyoscyamine is usually so hyoscyamine is basically found in this drug, Buscopan. I think you've come across it. So they usually muscarinic agents, and they usually have basically the effects of stimulating the parasympathetic nervous system, basically. So they're talking about the tropane alkaloids, basically atropine, hyoscyamin, and hyoscine. So they're found in this particular tropane class. So for the third class, we have the quinoline alkaloids. So they usually have a quinoline structure. So if you remember the quinoline over here, on the first row, the rightmost, this structure over here. So we have the cinchona alkaloids mostly, quinidine, being derived from that. I think chloroquine usually has the same structure as well. It's usually a 4-amino quinoline, if I'm not mistaken. And they're usually actually a derivative of this. Yeah. So examples of this, maybe the clinical uses for the cinchona alkaloids. Quinine is mostly used for malaria. Quinidine usually used for arrhythmias. It's actually a type 1A antiarrhythmic agent. Cinchonin and cinchonidine, I'm not really sure if they have clinical uses, but I think it would actually mostly be in malaria, if I'm not mistaken. So yeah. So isoquinoline alkaloids. So these ones usually have the isoquinoline moiety. So they basically include hydrastin, the D-tubocurarine, emetin, and some opium alkaloids. So D-tubocurarine is usually a non-depolarizing muscle relaxant. So yeah, they usually basically interfere with they bind with muscarinic receptors, causing preventing acetylcholine from binding. So yeah, usually that example. Emetin is usually used as it basically prevents vomiting. Hydrastin, I haven't come across it in clinical uses. So for the indole alkaloids, this type of alkaloids usually have the indole group. So these ones are also very common, and they usually have also a lot of clinical uses, and also some non-clinical uses. For example, ergotamine and the ergot alkaloids, they're usually used in migraine headaches. LSD is basically a narcotic. It's usually abused. Strychnine as well. It's actually considered a poison. I think it comes from the same group as emetin. Same plant, Strychnine naxivomica, is usually the botanical source of this agent. So basically, for here, you'll be looking at this second row. You'll see it as the third last, or the third compound over here. So this is in this type of alkaloids, they usually contain this particular moiety in one of the structures. So I've seen some questions somewhere. Basically, I'll just share them later. They usually ask you in this section, they'll just give you, or they'll ask you which of the following is not an indole alkaloid. Then they'll give you the examples, they'll give you choices over there, and you have to choose. So basically, you need to know basically the examples in each type of alkaloid, and maybe one or two things about it. If it has a clinical use, if it's poisonous, yeah. So those are most of the things that are usually looked at when asking questions from this area. So for the imidazole alkaloids, an example being pilocarpine. Pilocarpine is a muscarinic agent. It's usually used mostly to dilate the eyes during a fundoscopy when they want to basically look into the eyes, diagnose it if there anything, do some tests on it. So they usually use pilocarpine. So being an imidazole alkaloid, it basically has the imidazole moiety. So basically on this section, you really need to know the structure. So because sometimes they can actually give you a structure and then they ask you to give an example of an alkaloid in that class. So it's very important to know the structure apart from the clinical use or basically the pharmacological significance of that particular alkaloid. For the purine bases, caffeine and theobroma. So these ones, they fell under the group we called protoalkaloids. And we said they are not really derived from any amino acids, and they also they might contain the heterocyclic ring with the nitrogen in them, but their origin isn't from any amino acids. Yeah, so they usually have the purine structure. Basically, the purine is usually a fused ring. Yeah, so the indole and the imidazole ring, I think. So we have the phenanthrene alkaloids, which include morphine and codeine. So these are usually the opioids over here. They usually have that phenanthrene moiety. It's usually a kind of complex structure. So it mostly applies to this opioid derivatives. So for steroidal alkaloids, we have solanine and tomatidine. So tomatidine is usually found in tomatoes. Solanine is found in potatoes, Solanum tuberosum in most cases. So these ones are usually also not considered as true alkaloids. So they're usually a special type of alkaloid because they're steroidal in nature. So as we said initially, true alkaloids are considered to be derived from amino acids and to contain a nitrogen in the ring. So for the steroidal ones, they have a nitrogen in a ring, but they're not derived from any amino acids, as you know. Yeah, so for specific groups, we have the pyridine, piperidine alkaloids. And here, the most important drugs include the areca, which contains the alkaloid arecolin. We have lobelia, which contains lobelin. We have the peleterine from pomegranate. I think you've looked at this when you're looking at the naming of alkaloids. We have conium from conine. We have piperine, which is derived from black pepper. We have nicotine from tobacco, etc. So we look at lobelia. So the alkaloid that is found in this here is lobelin, and usually has expectorant properties. So lobelin will basically therefore be used as a respiratory stimulant, and it's mostly used for in anti-smokers deterrent. I haven't really come across this one. So they're saying it has nicotine type of effects and can be used as an anti-smoking agent. So it's also very important to know the source. That is the botanical source of this particular alkaloids. It's usually also very examinable. So conium usually contains the alkaloid conine. It's usually very poisonous. So the botanical source, I think, is usually Conium maculatum. Yeah, just confirm the species name, but the genus name is usually Conium. So I'm not sure if it's maculatum or yeah, but it starts with an M, basically. So they're saying the bean is used as an antispasmodic agent, and it's also a sedative. so the tropane alkaloids, as I said earlier, so they're usually very diverse in terms of the botanical source. So they come from different, and they also have very diverse uses. So for example, from Datura species, usually derive atropine itself. So atropine, is usually used in surgeries. It has very, very many clinical uses and as an antimuscarinic agent. So it has very many effects. So over here, you need to know the effects because sometimes you might be given symptoms of poisoning. So they usually cause things like, uh, it's not really fever, but what is the right term for this? Usually high temperatures cause the body to overheat. They cause you not to salivate because basically the antimuscarinic effects are usually from these tropane alkaloids. So we have Hyoscyamus muticus, sometimes Hyoscyamus niger. Usually we derive from this hyoscine, which is a spasmodic agent. We have scopolamine. So cocaine is usually a CNS stimulant, so and a local anesthetic. So if you look at the structure of hyoscyamin over here, you can actually see the tropane moiety. Okay, I can't highlight it at the moment, but yeah, so the topmost structure with the methyl nitrogen group over here is usually the tropane moiety. So all alkaloids containing that moiety will fall under the tropane class. So yeah, hyoscine, like we mentioned, spasmodic agent usually found in Buscopan. So basically, okay, they're just giving us an extraction procedure. I think this was covered in lecture of Alkaloids 1 by Stanley. Yeah, so they're telling us tropane alkaloids, they have a tropane nucleus. Okay, basically it's just a repetition of what we've discussed. So just know the examples, hyoscyamine, cocaine. Basically, those are the most common questions that will come from here. There are lots of repetition coming from here. So one thing you need to know about the tropane alkaloids, they usually basically come from the family Solanaceae family. So we also refer to them sometimes as the Solanaceous alkaloids. So they're telling us these alkaloids are usually restricted to the alkaloid of tropane nucleus. Yeah, so this is fairly mostly find the tropane alkaloids in this Solanaceae family. And so some members of the family Solanaceae contain non-tropane alkaloids, and an example is solanine and nicotine. So solanine is usually a steroidal alkaloid, as we mentioned before, but it's found in potatoes. Yeah. So potatoes are actually fall under the same family of the Solanaceae family, but the alkaloid is not really a tropane alkaloid. Nicotine also isn't a tropane. Basically, it's the five-membered ring alkaloid, in as much as it comes from the same family. But a majority of alkaloids from this particular family will basically be the tropane alkaloids. So giving us examples of sources, basically, I think you guys are familiar with managu. Usually they usually call it the deadly nightshade. Yeah, the nightshade. It's usually, they usually contain this tropane alkaloid. So we have also the datura, the hyoscyamus plant, scopolia, etc. So basically, the solar the most common source of the tropane alkaloids. Covered in lecture 1. So sometimes you will find different, the alkaloids more concentrated in the leaves. Sometimes the alkaloids will vary depending on the season. Yeah. So basically, they're just small things to note about. But I think it actually applies to all phytochemicals. The fact that they can be found in different concentrations in different parts of the plant, as well as occurring in different levels depending on seasons. So there's lots of repetition basically over here. But if you feel like I'm skipping something important, maybe you can just ask me to go back. So belladonna. So basically, this one usually comes from the genus Atropa. So Atropa belladonna. So it's basically the deadly nightshade, managu. If you I think you're more familiarized with that name, but I think we've really had enough with these alkaloids over here. So let me just find the next group of alkaloids. So they basically just went into describing.
Hello.
Yeah.
Wait, nini atropine ni
Yeah, nakusikia.
managu.
The podcast. So yeah, Atropa belladonna is usually the managu. So for the biosynthesis of the tropane alkaloids, I don't think it's really clinically significant for now. We can just keep it. Okay, so we have this other class, basically the quinoline alkaloids. So the quinoline alkaloids, as I mentioned earlier, so they usually have the quinoline structure. So it's usually two six-member rings that are fused together. So the quinoline moiety. So usually the quinoline moiety usually differs slightly with an almost similar. I'm not sure the other moiety that it's almost similar to, but you need to know the structure. So where the nitrogen is found specifically. So yeah, so I think we saw the structure earlier. We'll find it over here. So this is usually the quinoline structure. So it's very important to note where the nitrogen is actually located, because there's some other alkaloids where the nitrogen, it will have basically the same chemical structure, but the position of the nitrogen is actually shifted to I don't know the numbering of this particular point, but basically to the what you have in the next carbon on the right, but we'll look at them later. So for now, the quinoline alkaloids. So just note the chemical structure and the position of the nitrogen for this particular one. So the quinoline alkaloids are basically mostly the cinchona alkaloids. And from here, we have the cinchonine, cinchonidine, quinine, and quinidine itself. So we also have alkaloids from the family Rutaceae. They're giving us an example of casprin, which is derived from the Casparia bark. I haven't come across this one before. We also have the acronicin, basically. It's usually has some anti-tumor activities. I haven't come across it as well. Yeah, but basically they contain the quinoline structure. So the most common ones here will be the cinchonin, cinchona alkaloids, the cinchonin, cinchonidine, quinidine. I think those ones are usually very easy to note. So it will be important also to note these other exceptions, which are not so common, because sometimes that is the ones that examiners will go for. So in terms of the uses, quinine usually used in malaria. Cinchonidine is quinidine, sorry. It's an antiarrhythmic agent. Class 1 A antiarrhythmic agent. So usually they block sodium ion channels, and yeah, basically used for I think atrial fibrillation, if I'm not wrong. Yeah, so quinoline alkaloids, so the cinchona and its alkaloids are the only members of this group which are presently of therapeutic importance. So the other examples that you mentioned, including the one that had some anti-tumor activity, are not really in clinical use at the moment. So they are usually the quinine, quinidine, the cinchonidine, and cinchonin, respectively. So other alkaloids of lesser importance are, so they're actually about 20, which have been isolated from the cinchona bark, basically. So alkaloids usually occur in the parenchymus tissue of the bark in combination with tannic acid and cinchotannic acid. I think this was mentioned in Alkaloids 1 by Stanley. So basically the structure, so you can see the quinoline moiety over there. So this is cinchonin. So one thing to note about cinchona, the family is usually basically, the family is Rubiaceae. So yeah. So okay, so the botanical sources that are available here, we have the hybrid bark of the cinchona calisaya and the cinchona miracantha. So like I mentioned earlier, it's usually the geographical source also but not as much, and mostly the significance of that particular drug. So quinidine, as I mentioned, it also has some anti-sodium ion channels. Yeah. So yeah, so maybe class. So the chemical tests done for this to identify them is usually the thalloquine test, ammonia. So you usually moisten the drug with glacial acetic acid, then you heat it to ignition. So then blood red drops usually condense on the sides of the test tube. If you have these things being present. So I think usually for these tests, it's usually just important to know what can really be asked, not really the process, but the type of test that is done and the results that you expect to see. Basically for all these phytochemicals. So just know the test and then the results that you expect from it. So for the Harlequin test, we usually expect we still use bromine over here. So yeah, maybe the reagents being used can also be asked sometimes, but yeah, we still use bromine, ammonia, and the expected result is usually a deep green coloration over here. So the isoquinoline alkaloids, oh, I haven't given examples. So they're telling us the isoquinoline structure occurs in considerable numbers of alkaloids and is widely separated families. So the isoquinoline usually has
Sam.
chemical. Yeah.
Yeah, I think isoquinoline, I think we can start on isoquinoline tomorrow. Tumalizie hapo kwa quinoline. Ndio we don't nini with a lot of content. Tulikuwa tumalizie kwa quinolines today.
Oh, okay. So.
Yeah. But thank you so much. Imetupeleka vizuri sana. Mimi sikuwa najua managu ndio atropa belladonna. I'll start abusing managu seriously. I hope Chai has heard the meaning of that. Stano, back to you.